It's very quiet. Everybody very excited about this talk, I guess. Or already asleep, maybe.
Yeah.
So today we have Ricky. Ricky is an ASB postdoc here at HAO. Ricky comes here through a somewhat convoluted path. He did his undergrad in Minnesota and then spent 7 years working at CERN, after which he decided to get back into science and did his PhD, well, sort of physically here, but technically in Montana, Bozeman. And then he got this ASP postdoc position here a couple of years ago. So he's going to talk to us about sun-like stars, so a bit of the solar-stellar connection today. Thanks, Albert. That's your microphone.
I think so. All right. Okay, good now? Right, so this is some recent work that I'm sharing with you all. I'll do an introduction in the beginning and then get into some ways that I've been using TESS data that's only been available since December. And my list of collaborators there on the bottom is under the purview of this TASOC project. So it's this is the TESS astroseismic community. And there they have a wiki page where people post projects and you sort of ask if people want to get involved. And a large number of people wanted to get involved and have been very helpful in putting this together. So thanks to all of them. And special thanks to the ones that are underlined. I've had a lot of exchanges with them to develop this work. And that's Rafael Garcia, Rene Kiefer, Savita Mathur, Travis Metcalf, and Angela Santos. So my interest is in the dynamo. And we know that the sun has a cycle. We've been observing sunspots for a good number of years, as you can see here, in this reconstructed group number time series. And most of the time, the sun is pretty regularly varying with its roughly 11-year period, although the amplitude of its, the peak of these cycles can vary by, up by a factor of 2 or more in some cases. And then we have this different phase of variability, the modern minimum, where the cycle sort of petered out and disappeared. It's a very curious thing, and I like to study the dynamo because of all of the interesting things that the sun does on the surface that receive a lot of attention. I mean, the dynamo is ultimately responsible for all of it. So the question is, where does this magnetic field come from? Why does it vary in the way that it does with this regular cyclic period? And what are the physical mechanisms thereof? So the problem with studying the dynamo is that it's operating in the interior where you can't easily observe. And so we're sort of looking at how it's operating through the surface without being able to look at the physical properties directly, which makes things more complicated. But one encouraging fact that I've taken advantage of is that the sun is in fact a star. You can see that it looks similar to the other stars in this picture. And the idea behind most of the work that I do is that these other stars provide additional dynamo experiments. We can use these to understand how the dynamo works and how it evolves over time. In particular, it helps answer the question, what sort of magnetic properties happen on stars in response to the physical conditions. Different masses, which result in different convection zone depths, different rotation periods. Example, all of these are sort of inputs into the dynamo problem. And then the magnetism and its subsequent variability is like the output of the dynamo problem. And so we get a statistical sense of how dynamos operate. And this has been known for a good long time. And in this seminal work here in Baliunas 1995, I think we got the first really good look at all of the different varieties of variability of magnetism on stars. And this comes through the proxy of magnetism in the calcium H and K lines, which I'll show in the next slide, through this S index. But basically, it's a well-established proxy for integrated unsigned surface magnetic flux on the unresolved surfaces of these stars. And you see in the left column, you see these types of stars. There's a 25-year time series. the ones that are not cycling, which is not like the sun, except perhaps during the Maunder minimum period. So those are the flat stars on the top left two panels. There's sort of this long-term trend of variability, but they look mostly flat. There's a classification called VAR, which means they did a period search, but they didn't find anything significant, and so they vary sort of erratically. And then on the right, you see different qualities of cycling stars, starting from worst to best. And if you look at the ones that are classified as poor and fair in this work, it's hard to pick out where the cycle is, whereas the good and the excellent ones look rather sun-like. Okay, and I do not believe this is a signal-to-noise problem. If the sun were observed as one of these stars, its signal would be clear as day. The measurement uncertainty is of order 1%. The variation in calcium is of order 10% or more. So if a nice pure cycle were out there in a sun-like star, this would have been able to see it. There's also more interesting cases of multiple cycle periods taking place at the same time. So this one has a 17-year period and a relatively consistent 2.6-year period you can see in this time series. So this comes from the S index, and this is just a spectral zoom from the current spectrum of the calcium lines. And the S index is defined as the ratio of 1 angstrom bands in the H and K line cores, the flux in those bands, over in the denominator these 20 angstrom V and R bands. And a variant of this same index is called R prime HK, and there you take out the color term that's introduced in these V and R bands. So if you have stars of very different effective temperature, you're basically going to be changing those denominators, not from anything due to the magnetism, but due to the fact that there's just less or more flux in those bands. And so the R prime HK uses empirical relationships to put these in terms of the bolometric flux. And there's been a number of very interesting results from studying sun as a stars. One of my favorites is this one from Andy Szymanich here at HAO. And the upshot is stellar rotation and magnetic activity decrease with time. And here's his wonderful paper, 3 pages, and I think if he would have made the figure a little bit smaller, he could have got it in 2. But it's a wonderful, concise result. It's received a lot of citations, and so people continue to study this problem. And here's the data. The figure is showing lithium abundance, rotation period, and the calcium HK magnetic proxy for 2 clusters, Pleiades, Hyades, and the Sun. And right, with 2 points you can make a line, and with 3 points you can make a fit. And sure enough, with the fit to the 3 points, you get the now it's called the Szymanich spin down law, which is that the rotation period increases as the square root of age. And the rotation period, yeah, and you also see that the HK proxy is doing something similar. So another interesting result was in my thesis when I went and looked at those classes of variability with respect to the Rossby number, which is a key parameter for the dynamo. So in this plot, just ignoring all of the colors, you can see that activity and Rossby number, which is the ratio of the rotation period to the convective turnover time, which is a parameterization of the convective speed in the star, and that's model-based. But so if you don't do a sort of dimensionless parameter study, then the activity does not make a nice relationship like this unless you have a very small temperature band. So all stars of the same mass, basically all stars of the same convective depth. When you mix stars that are with different masses and different convection zone depths, and then it just becomes a crazy scatter plot. But in terms of the Rossby number, everything falls into this nice relationship. And what I noticed when putting this sample together, which is combining that Bally-UNIS 95 sample with rotation periods from the literature so that I could get their Rossby number, is that the sun basically shares in common its nice, simple excellent class cycle with a bunch of K-type stars. And in that sample of about 100 stars, there were no other G-type stars that had a sun-like cycle. They were all more complex than the sun. They either had two cycle periods or they were radically varying. And so one thing you can take away from this is that long-term variability decreases with complexity with the Rossby number. So that things are getting more simple to the sort of sine-like behavior of cycles, or those gray-toned ones, which are the long and flat, which don't do much.
Can I ask a question?
Yes.
In X-ray relation, X-ray versus Rossby number, there are some saturation regime.
Yes.
And how do you think about this figure?
Very nice question. So a lot of people say there's a saturation regime in the calcium data at, well, roughly on this plot, Rossby number a little bit less than 1, where you can see it gets horizontal. But then you can see in this sample it hooks up again. And that's a few stars. In later slide, I add another star to that from another sample. So I think that's a real thing, and I think there's sort of a saturation that only goes so far. And if you rotate sufficiently fast, you get increasing activity again. Okay?
Yeah, just a comment. I think it'd be useful, maybe you've already done it, to separate stars by spectral type or effective temperature and such, because for one reason the saturation regime begins at a different Rossby number as you go through the stars at different spectral type.
Right.
And that might mess up that diagram because you put together stars of many different spectral types.
Right. Yeah, so these are F, G, and K-type stars, and the diamonds are K-type stars, the circles are G-type stars, and the squares are F-type stars. So in fact, that hook that goes up is 3 K-type stars. So maybe there is something to that. Something else that's interesting and new in this diagram is the huge amount of scatter at low activities. I'll talk more about that later. And this one shows, again, this sort of concept of stars their variability becoming simpler over time. These are all on the same scale, and this is in the S index, and these are all very sun-like stars. They're within 5% of the sun's effective temperature. The top two have a much higher mean activity and much more complicated variability than the sun does. And so even our worst, most spot-filled, active, flaring CME day on the sun is not as bad as the quietest day on these other more faster rotating stars. And there I give you the rotation period and the estimated age. A little bit of a cheat on the bottom there. That's a subgiant. That's not quite the solar mass. And the reason is that my temperature selection basically took in some of these subgiants. If I wanted solar mass subgiants, I would have had to have allowed cooler stars. But I can tell you that there are solar mass subgiants that are just as flat inactive as that one. I don't have them in that plot. And now I'm going to end this portion of the talk with a little bit of a sad story and a sort of cautionary tale, or a place of opportunity, perhaps. The future outlook of these dedicated long-term synoptic programs, which made those previous plots possible, is pretty bleak. So the Mount Wilson Observatory already finished. So that one ran from 1966 until 2003, and it has about 100 and 300 synoptic targets, depending on what your definition of synoptic is. So running that whole span, you've only got about 100. If you want a couple decades or maybe 1 decade and you're interested in giants, they have some stars in their archive for that as well. The solar stellar spectrograph that was developed here at HAO and installed at Lowell Observatory has been running since 1994, but that's probably going to be ending in a few years' time, based on discussions with the director, Jeff Hall. That has about 100 synoptic targets, very close parameter range to the sun effective temperature. So those are not FGK type stars. Those are mostly really G type stars. So there's a lot of interesting data there that will be analyzed soon. And then the Fairborn Observatory APT program does not H and K, but sort of medium band photometry in these B and Y bands that's been operating since 1993. And based on discussions with them, that one is also nearing the end. And these are very unique data sets. If you want to look at long-term cycles of other stars, this is really the only place you can go. So it's sort of sad, but there are lots of archival data that is waiting for detailed analysis. So I think once these data get published out there, a lot of people will grab onto it, and there's a lot left that can be done with these data. But in my experience, the big problem with these numbers, well, it seems like a lot, like, wow, 100 stars. As soon as you start dividing this up by anything, effective temperature, metallicity bins, rotation bins, you have 1 star left. So asking the question like, oh, do all stars that are really in the solar parameter regime, including rotation, have a cycle like the star or activity, a cycle like the sun or activity like the sun? These data sets are really inadequate for that. But today is actually the era of humongous statistics in photometric variability. And that's due to these exoplanet searches. So we have 2 space-based missions, Kepler and TESS. I'm sure everyone here has heard a lot about them. Kepler launched in 2009. It operated on 1 field for about 4 years. Then its reaction wheels broke, and it started moving across the ecliptic, sampling different fields for 90-day periods. TESS just launched last year. It was in April 18th, and its first data has just been released. I'll explain the cadence of TESS in a bit here. Well, it's written there. So basically with Kepler and TESS, you get these very wide bands. This is the full width at half maximum of their band passes on the sun spectrum. TESS is a little bit redder than Kepler, and I think that is to get rid of the troublesome blue, which introduces too much stellar variability when you're trying to search for very small planetary transits. But anyway, there's a huge number of stars. So Kepler observed 500,000 stars. TESS is going to do the same for the whole sky. The cadence is very good. The duty cycle is basically 100%. So with Kepler, you get 30-day full-frame images, which you can sort of compare on the photometry in an absolute sense. TESS, you get full-frame images on a 30-minute cadence, so you can do absolute photometry at a much higher cadence than you could with Kepler. And then you've got the 30-minute and the 1-minute light curves that you can do, rotation studies or astroseismology with on Kepler. And on TESS, you've got at best a 2-minute cadence for those purposes. Here's the fields. The Kepler field is about 116 degrees squared. The original Kepler field that it stared at for 4 years. And then on the bottom are the K2 fields going across the ecliptic. I think there were 13 of them. And so on the top you have a set of stars that you have time series for 4 years. On the bottom, about 90 days time series. And the TESS field is the whole sky. But it's in these sectors, so you can see those sort of rectangular bands, sort of the lines, the gray lines in the blue. I think I show this better later, but they're rectangular bands, and each one of them is sort of stared at for about 27 days. And then where there is overlap, you can construct sort of multi-epoch time series that'll go longer, up to a full year, where TESS will switch from observing the southern ecliptic to the northern ecliptic. The most interesting thing I think that has come out of the photometry deluge so far is basically the breakdown of the managed law that I just showed you. The left is a paper from Jennifer Van Saters in Nature, which uses ages obtained from astroseismology, made possible with Kepler. And so you can observe the P modes of other stars and very carefully fit those to a stellar structure and evolution model, and out of that you get an age. And it's among the most precise methods of aging stars that are available today. And the upshot is that the Schumannish law, which is P rho proportional to T to the half, doesn't fit these stars. And these are all old stars, and that's not an accident. Astroseismology is biased towards old stars because of the magnetic activity. Young, highly active stars have too much going on their surfaces to detect these P modes effectively, right? So the old quiet ones get their ages measured, and they don't fit what has been observed before in the rotation law, basically from cluster. So the other way to get ages is membership with a cluster. Then you can, all of the stars are the same age, you fit a stellar isochrone to them, you get the age for every star in there. So the data fit if you stop the magnetic braking process at a critical Rossby number of about 2. I think it was 2.1 in that paper. And then the star doesn't slow down anymore. And then those gray bands show model results, taking that assumption in and accounting for the various ranges of masses that are in those panels, right? So then those models fit the data, whereas the black line, which is the Schematic law, or a normal braking law, which is the Schematic spin down for most of the main secret life, and then a spin down due to expansion, basically conservation of momentum, takes over after that. So an additional piece of evidence from that came from this Kepler rotation search, where over 34,000 stellar rotations were measured. And you can see this temperature-dependent upper edge, right? And so the question is that, did the stars all stop spinning down at that point? The bottom panel shows histograms, and you can see sort of the sharpness of that edge. So those are temperature-bend histograms showing that rotation period edge. And the little red point is the sun, which the thing that you learn when you get into the solar-stellar connection is if there's ever an interesting transition point in anything, that's where the sun is at, okay? So here it is again, right on this edge where apparently the magnetic braking breaks down. Or does it? So Van Seters had a follow-up paper where she did a forward model from stellar structure models. Phil, did you have a question?
Yeah. Well, before you get into this one, can you go back one?
Yeah.
So, if the stars were able to give you a harmonic of the rotation instead of 2. So if stars on the left-hand panel, would they fit the Schematic law if you doubled their rotation periods?
You mean the left-hand panel? Okay.
So I mean, if
I don't think all of them would. I've never heard of anybody trying that. But it would be really strange to have all of those stars off by harmonic,
isn't it? It's not a harmonic.
Yeah.
So okay.
Okay.
So you're fairly convinced that the rotation periods are the error bars are credible there on those points, and
right.
that they really do depart from the Schematic. I mean, the Schematic was just empirical on 3 points.
Right.
I'm not saying I believe it for everything, but I wanted to know how secure that result really is.
I think the rotation period is secure. The question that is debated is, are the ages accurate? So, as I said before, this is a specially biased sample to old stars. There are no old clusters. So you can't compare cluster-based ages to astroseismic ages yet.
So there are no old open clusters because they've dispersed or something? Or?
Right.
So you just have local...
By the time you get to the age regime where astroseismology works, there are not clusters.
So you end up with a moving group as
right.
opposed to a real isochrone situation. Okay, thank you.
So this was Van Seters' forward model. So it uses a galactic population synthesis code called Tri-Legal. And then it takes all of those stars and applies her evolution and rotation models to it under 2 different assumptions. One of them is that the rotation stops at this critical Rossby number of 2. That's the bottom panel. And the other is that there's just a detection threshold of some kind, that the rotation, that the surface modulations in these stars become so small that Kepler can't detect them anymore. And you can get the same result with either assumption. But of course, there's very different implications in those. One of them, the stars that actually stop their spin down process. The other one is also potentially intrinsic. It depends on the nature of the detection threshold. So one possibility is item 3 here. The braking continues, but surface features diminish smoothly in a temperature-dependent fashion and reach a Kepler-specific detection threshold. And if you had a more sensitive photometry, you would still be able to detect their slower rotation periods. The other possibility is that braking continues, but the surface features diminish abruptly in a temperature-dependent fashion, and there's a universal detection threshold. That would be something akin to like all spots, all surface features disappear from these stars at about the same critical Rossby number, and then you have no hope of any sensitive photometer detecting surface modulations. And the number two one is I'm going to focus on for the rest of this talk, that stars actually stop braking at a critical Rossby number due to an abrupt change in the surface field strength. That's not the leading hypothesis. The one that's talked about the most is the first one, is that there's a change in the magnetic topology, which makes the basically you go from a dipole moment to smaller scale fields, and that's what changes the rotation period, the spin down law. While making this talk, I realized that this plot also gives you an insight into that. If the braking stops at a critical Rossby number, I should not observe any stars that are beyond that critical Rossby number of 2. Here I've circled 4 of them, well 3 plus 1 maybe. They might all 4 be maybes because measuring rotation period at these low activity levels is very difficult. So it would be interesting to go through these very carefully and ask myself whether I really believe those rotation periods and whether I really believe the Rossby numbers. The other stars that are beyond that Rossby number 2 line have a dot in the middle of them that indicates that they're a subgiant. And for that, I'm sure that this empirical Rossby number law that I'm using in this paper is wrong. And so those could be anywhere in this plot. And so one would have to more carefully model the Rossby number for that set to see if, in fact, you see the braking stopping. But you can see the sort of pile up at the Rossby number 2 line. So, maybe there's something to this. Go ahead.
To calculate a Rossby number, you need a convective turnover time, right?
What's that?
To calculate a Rossby number, you need a convective.
That's right.
So where do you get that?
So that was originally done with stellar evolution models. It's model-based. And then it was turned into an empirical law which basically fits this distribution the best. Right? So you have a convective velocity at 1 pressure scale height above the tachocline, above the base of the convection zone from the model. Then you have a free parameter that's alpha, and they found that alpha equals 2 makes this relationship the best, which they liked alpha equals 2 for other reasons anyway, so they were satisfied.
Okay.
Right, so the question is, can we detect a magnetic counterpart to the critical Rossby number? Well, how are we going to do that? We need to know something about the magnetism. And that leads me to this question. How does one study magnetism with photometry alone? And actually, I'll tell you a little story. I had a NASA proposal rejected because I answered this question in the negative. I said, you can't study magnetism with photometry alone. So my proposal was to make this solar stellar database that would have all of these observational properties of stars where we know something about their magnetism. And I didn't say anything about Kepler stars. I said, Kepler's great for astroseismology. You can characterize the mass and the age and things like that. And you can characterize its rotation period. But these are all inputs to the dynamo problem, which was the scope of this database. So I said, Kepler's not interesting because those stars, for the bulk majority of those stars, you don't know anything about their magnetism. But the real answer is yes. And I should have known better because people have been studying magnetism with photometry for over 400 years. You just look at the spots, right? And so that's, easy enough on the sun where you can, resolve it with your eye or a small telescope. But for a star, you collapse this thing into a light curve and you get the same thing, right? So when there are surface features, whether they be bright faculae at the limb, which if the contrast is good enough you can see in this movie, or the dark spots, you get modulations of the light curve, and that is connected to the underlying magnetism. The question is, how are you going to use that information in a 1D light curve? And people have come up with different ways to do this. Early on, Bosri 2013 had this R-var parameter, which is basically just the amplitude of the whole light curve. So the idea is that, whether you have one giant spot that's causing a huge modulation or one side of the star that's got 1,000 small spots that's causing a huge change in the modulation. Either way, when you have this huge change in the modulation of the light curve flux, you've got something that's connected to the surface magnetism, something that's connected to the spots, something that's connected to the magnetic features on the top of the star. Mather in 2014 came up with this other idea, is that you just use the variance. You use the standard deviation of the light curve, binned by 5 rotation periods, okay? And this is something that's typically done a lot on the sun. You sort of average things over n of the rotation period. So in this case, it's 5. Then you subtract off the photon noise from the detector. And in this star that she's showing here, you can see that this SPH metric, so photometric activity metric, sort of varies over time. And those bars indicate the solar excursion. So this is a star that is more photometrically variable in the Kepler bandpass than you would expect the sun to be. But you know, these proxies in these early results didn't give a lot in terms of relationships with respect to other things, so they sort of could be seen as kind of rough. So on the left from the Bostrey paper, you have the R-var with and rotation period, and although you can see that there are no sort of, so there's a deficit of sort of inactive, so small R-var stars with short rotation periods, it's a pretty blurred distribution here. And on the right from Mather, you again see with the relationship with the rotation period, and the red diamonds are all stars of roughly the same spectrotype. So you can see some hints of a trend there. All right, so that maybe there's something to this. It was done with the sun as a star. It's always best in these solar-stellar connection studies to validate every technique that you have with the sun. And so this was done with the Virgo sun as a star photometry on SOHO. So there's a good number of years of Virgo photometry. You do 5 rotation periods, which is what's that, roughly 120 days, 125 days on the sun. Take your standard deviation bins, and then there on the bottom you can see that it correlates quite well with the sunspot number. Although there's some hysteresis effects that he interesting hysteresis effects that he discusses. It seems that the declining phase tends to be more photometrically variable than the rising phase. But nonetheless, it tracks well with the sunspot number and several other solar activity proxies that he studied. I was a part of this work, Salibert 2016, that has a set of Kepler stars that had the mean SPH, the photometric activity proxy, and some limited HK observations. The problem with Kepler stars is they are faint, right? It's staring at one field, so you get 1 or 2 sort of normal eyesight bright stars, and then most of the stars are magnitude 12 to 14, right? And so you're looking at very expensive observations to get HK, which is already faint to begin with, for these very faint stars. And so there are not a lot of HK observations for Kepler stars. Okay, but nonetheless, we put together this sample, and it looks like there's some hints of a trend between SPH and calcium HKS. So the goal, calibrate a photometric activity proxy to the established HK emission proxy. All we need is a sample of stars with HK observations and high-cadence precision photometry. Again, I said difficult with Kepler, not difficult with TESS, because TESS does the whole sky and it does bright stars. So there is no bright magnitude limit for TESS. So basically, all of the 5 and 6th magnitude, 7th magnitude stars that have archival HK observations are going to get a precision photometric time series with TESS. Okay, and that's where we go with this. TESS first light, September 17th of last year. So this is showing it's 4 telescopes, and each of them has 4 CCDs, and it just observes everything, right? So everything in the field, and you set up, just like for Kepler, you set up little pixel masks. They're big pixels. I don't remember the exact number, but you're sort of limited in your number of targets by how big these pixels are. And then you, with that pixel mask, they send back the light curve. So they integrate. Sorry, you get the full frame images every 30 minutes, and then you get these faster 2-minute integrations from the spacecraft. that are used for astroseismology. So TESS's first data release from sectors 1 and 2 of the southern ecliptic that are shown here were released on December 6th. And I had already put together my huge sample of HK stars and submitted a TESS GI proposal, which was rejected. It was not interesting work. Sorry about that. But anyway, there's 72 stars in these first sectors, and let's see what we can make of them. So here are the stars, and their calcium HK levels in the log R prime HK proxy, and then their B minus V. So the sun is, B minus V of about 0.65. You can see there's quite a cluster of stars around the sun, and there's no rhyme or reason to this selection except that the data exist. Okay, so these are most of these are from planet search surveys that are doing radial velocity, and they just happen to get calcium HK as a byproduct. It doesn't make for the best time series sampling because they're not dedicated towards getting a regular sample over a long period of time, but I did make at least a selection that there's at least 5 observations and that their duration is spread over a year to try to reduce the sort of scatter of decadal scale variability that may exist in these stars. Here they are on an HR diagram. Most of them are main sequence. The line of open white dots delimitates the end of hydrogen burning, so that's the subgiant phase, and so you can see there's some that are past that, so a few subgiants, mostly main sequence, a lot near the solar mass. Here's the photometry. The top panel shows the sort of the raw integrations, and then the bottom one is when they try to remove all of the systematics, and they use that using a principal component analysis. So they look at basically pixels that are all varying in the same way, typically due to things like thrusters firing and pointing corrections that make glitches in the photometry appear, and then you can see how these glitches all sort of disappear on the bottom panels. And in these two frames, you can see how the glitches are the same. So yeah, these ones are probably next to each other in pixel space. And so they're removing the same things in the top panel. The other thing to point out here is, these first two are varying, by like 5%. So that's a huge photometric variation. This next one here is, 2%, still huge. Clear rotational modulation. You could sort of go and measure the rotation period with a ruler on these ones. And then you get ones like this that don't vary very much, and you wonder if there's a rotation signal at all in there.
Can I ask a question about
Yes.
first light curve? There are some tiny brightness increase, especially in the first. Yes, this one. Are there flares?
I bet they are. Yeah. Yeah, TESS is, look at this rotation period. So the bottom axis is in days. The tick marks are at 5 days. So it's less than 5-day rotation. This is an extremely active star, and the flares, I'm sure, are popping off quite frequently. Okay. So here is the main result. Activity-activity relationship. On the y-axis, we have the tried and true calcium HK proxy. On the x-axis, we have the sort of questionable but probably should work photometric activity proxy. That is the standard deviation of these light curves over 5 rotation periods. Caveat, we only have 27-day time series. A lot of these stars are going to be rotating at even longer than 27 days. So in most cases, it's just the standard deviation of the entire 27-day light curve. Okay? And the interesting thing in this plot is that, so every point here is a real data point, but the ones that are big and with colors are the ones that one of the rotation search teams said, yes, either yes, there's a rotation period in this light curve and I found it, or there's not. I'm not confident about reporting the rotation period, but I'm sure that the modulations that I'm seeing are due to rotation. And that selection of stars made a very nice relationship. So the thing is, you have to be sure that your light curve is showing you rotational modulations. Otherwise, it appears that this correlation does not hold. All of those gray points in the bottom there are ones that this team said there is not rotational-based modulation in these time series. And then the question is then why is their SPH higher than the trend? Well, maybe those ones are dominated by sort of systematics, the principal component analysis that's used to reduce these data and remove those glitches may actually also introduce variability that is not real. And so it's a possible explanation for that. I had a lot of help. So I actually had 4 rotation teams of people volunteer to go and look at this sample and try to measure rotation periods of them. So team 1, I already showed you part of the results. They used autocorrelation method, wavelets, really the whole spectrum of ways to do power spectral density estimation out of time series. And they used their expert knowledge. So they looked at the time series and decided whether or not they believed what their tools were telling them. The other ones were more automated, but they're all using similar things: autocorrelation, Lomskargel periodogram, wavelets, combinations of them. And the thing is, when they reported a rotation period, it was almost always, I think only a couple exceptions, the same rotation period that other teams had reported. Where they differed in opinion is whether they dare to call that a rotation period or not. So the ones that are on the bottom of this panel are a declaration, no rotation period in this time series, all right? And so you see it's like sometimes they're unanimous, they're all saying there's no rotation period, or they're all saying there is a rotation period, but most of the time there's some disagreement. The upshot is detecting stellar rotation in 27-day time series, stellar rotation being of the order of weeks, multiple or 5 days or so or more, it's going to be hard and controversial. But and it has a consequence. So we've made the 4-team consensus after sort of comparing all the results and sort of deciding, okay, one team says this is not a rotation period, but the other 3 did. Okay, let's call it an unsure rotation period anyway. I didn't go through the legends on this, so let me go through that. On the left panel, that's only team 1. Okay means that they're confident in calling that a rotation period. Short means it sure looks like a rotation period, but the period is comparable to the 27-day length of the time series. So it looks good, but I sure wish I had more data. The other ones, weak, they said it's not I wouldn't report a rotation period for this, but I'm sure that the modulation that's in this is due to rotation, okay? On the right, it's a little bit different. Okay is basically unanimous. Every team is reporting the same rotation period. And unsure is basically usually one or more teams saying that I'm not confident about calling this a rotation period. And the result is that with that sort of more broad selection, you get points that are off this trend line, okay? And so it's not as good. And the question is why? Why is that? So this is team 1's rotation search tool, again, using wavelets, using autocorrelation. That's in the middle panel. They look at the Lomskargel, but they don't figure it into their thing. They have different confidence level thresholds for all of these, and it has to satisfy their thresholds in 3 different estimation techniques before they call a rotation period. Then on top of that, they go and look at it and say, are we really sure that's a rotation period? And in answering the question is, why was team 1's correlation so much better than all the others? I just took a look. I said, the thing that must be different is they're all choosing different confidence level metrics, right? So let's just sort the data according to these confidence level metrics and see how good the correlation of those top N sort of that top N sample looks. And you get plots that look like this. So this is team 3. This is the Lomskargel peak height metric. And in this metric, which goes from 0 to 1, basically 1 is a perfect sine wave, and then it just gets worse from there. And so if you set the bar at, say, 0.4, you get a correlation, a Pearson correlation of about 0.9. They set their bar at 0.2, right? So it's a lower bar, you get a lower correlation. You're selecting more of those stars that are sort of off the trend. One of team 1's metrics was this height of the autocorrelation function peak. So it's the first peak in the autocorrelation function. And you can see that steep rise sort of shows that it's extremely effective for selecting stars that lie along this correlation. They set their bar lower at about 0.3, but if you set it at about 0.4, you'd see that you'd be getting, roughly, I think that's about 25 stars that have a correlation of 0.9, and that's what that looks like. So I'm confident that using a technique like that, you can select the stars that have this correlation automatically, and that's very good. Because we're going to be doing things in mass in the future, so you want to be automatic. And so this is sort of the dashed blue line is the old fit to the Team 1 data, and the red one is that threshold where the height of the autocorrelation function is above 0.4. It's basically the same, and then the things are color coded. You can see that the most active stars have the largest height, and then and then it just sort of goes down from there. It doesn't select everything along this trend. And that's the remarkable thing about what Team 1 did. They didn't know about this. They didn't have the HK data. So this was blind. They were just looking for rotation periods from the photometry. And their selection just turned out to be awesome. And so they had this automatic procedure that I sort of described. They had these three metrics. So the ones that were the large black points here are their automatic selections. And then they went and looked at each time series and sort of talked amongst themselves about what they believe. And they ended up almost making it perfect, almost selecting everything along that line. There's only, I think, 2 points that they didn't select, and they got rid of stars at their automatic procedure that were off this correlation, and basically, after looking at it, said, like, no, I don't think this is rotation. And so another interesting thing is that this being along this correlation line, which, as we discussed, is an indication that there is modulation in the time series that's due to rotation, doesn't mean that you find the right rotation period from this. You have to be a little bit careful about this because, what is the right rotation period? All right. So on the right panel here, I've got that sample that I showed earlier in the talk, Rossby number and R prime HK on the y-axis. Those light gray points are Mount Wilson stars, and for a lot of them, so there's like 3 decades of observations in HK, which is a higher signal to noise. Proxy, better to find rotation period, and plus they got a lot of data. So I'm pretty sure about those rotation periods. And there's almost nothing in that no man's land right here, where all of these test stars are showing up. So I think you're sort of safe to say that I don't believe any of those rotation periods, although you never know. There's more statistics. Maybe there's something interesting there. That red circle on the right plot is one Mount Wilson star, very low activity. It has a very low Rossby number, but I'm almost sure it's wrong. It's probably a subgiant. And so there's a lot of investigation to be done, I would say, in how sure are we that everything falls along this previously established trend. So those are highlighted in green. The ones that fall along the Rossby number activity relationship are highlighted in green. They're mostly the high activity ones, which shouldn't be a surprise because those are the fast rotation ones where you would expect that it's possible to measure the rotation period, and that's what's shown in this plot. So on the x-axis is the detected rotation period reported by the 4-team consensus, and on the y-axis is the empirical rotation period, what you would expect just from the HK activity alone. So you're looking at this line. You've got HK for all of these stars here, and you look at that light gray line. That's from Mamajek and Hillebrand, 2008, where they basically came up with an empirical activity rotation relationship. So then you get your expected rotation period, and you can see that for almost all the stars where you should be able to see, we expect to see 2 rotation periods, they got the right rotation period. Okay. There are 2 on the left that were reported as non-rotation. It'd be interesting to look at if any team did say that there was a rotation period and if that one was, in fact, the correct one. And then there's only 1 star, which is arguably a harmonic. So that's on the P rho equals twice what you expected. And harmonics are sort of expected when you have surface features that are on one side of the star and on the other side of the star. It looks like you're getting twice the rotation period. And so you expect that can happen.
So the subgiants you were talking about earlier, is there rotation seen in the subgiants?
I don't know. I haven't looked specifically at the subgiants.
Okay.
I would expect that only very special high mass subgiants would still have a rotation period that would be fast enough to be detected with TESS. Yeah. That'd be interesting thing to check. Okay, so wrapping up, why does any of this matter? HK data can be used with caution as a prior in sort of the Bayesian sense for TESS rotation period searches with short photometric time series. Basically, if you have HK data, you have a rotation period that you expect. You see it in the photometry, and then get the real measurement, to sort of eliminate the scatter. That could be a useful tool for building up samples of activity and rotation. The photometry itself, SPH, can also be used as a prior because, as we've seen, under certain conditions of the light curve, it is a proxy for HK activity. Therefore, it's a proxy for rotation. Therefore, just from the photometry alone, you could look at it, measure the SPH, say what rotation period would I expect from this SPH, and does the measured rotation period seem close to that, or is it a million miles off? Again, it needs to be used with caution because we don't know exactly what we're going to get with larger samples. But the upshot of all that is much larger and more reliable activity rotation samples can be obtained from TESS and Kepler to study dynamo evolution and develop age proxies via astroseismology. So TESS is going to observe all of these stars with a 2-minute cadence. There's going to be a lot of potential for astroseismic ages, for calibrating both HK to age and rotation period to age, or SPH, the photometric activity to age. Measuring age in stars is very difficult, and this could improve things a lot. And below I have some statistics. I estimate there are 5,000 stars that have at least an HK snapshot in TESS. The largest activity rotation sample that has been presented to date is 167 stars. So lots more statistics. We'll get a lot better understanding of these relationships. And so far as the dynamo is concerned, a little byproduct from this work, I was just interested in the expected variability in the SPH metric due to the fact that we only have a snapshot of it. So as I showed in one time, for the sun in particular, you take SPH over time and it rises and falls with the solar cycle, right? What is that variability? We only have 27-day time series, so we're only getting a snapshot, and there's going to be intrinsic scatter due to the fact that we don't have decades of data for this. And when using Kepler data, which has 3 or more years of data, this is from Angela Santos' sample. She's got a paper coming out soon, which is doing rotation and photometric activity for the entire Kepler sample, which is going to be awesome. You get this relationship between the standard deviation of the SPH metric and its mean, right? And it's a linear relationship, okay? So to a point. So on the high activity end, log SPH greater than 2.5, on a log scale, the slope is 1. And so it's a linear relationship. That's exactly what I found in my thesis using HK data, that the amplitude of the S index for my sample of 27 stars with 50 years of data is linearly proportional to the mean. And this has implications for the dynamo. It's basically saying that the change in surface magnetic flux on the surface of stars is proportional to the mean. And I think that's a very nice constraint for dynamo problems. All right, so wrapping up. So this is going to be my goodbye colloquium. Like, hi, I'm leaving, my postdoc is up. But HAO actually decided to hire me as a project scientist to work with Hinode and Miriam simulations and doing some really tight, interesting integrations with those. And so thanks to HAO for additional time here, and I'm really excited by these new projects. And I'm looking forward to it. So the conclusions here, it's an open question whether this magnetically driven spin down of stars is real, but I think we're going to have some more data to sort of test this thing. It's going to be very useful to have a robust photometric activity proxy because there are so many stars, right? So the more you can do with photometry alone, the better off you are, because these HK observations are much more expensive. And so yeah, I think a proxy can be developed. It's all looking encouraging with just these first 2 sectors, and there's already 6 more sectors downloaded. But I can't redefine my sample all the time, otherwise I'll never get anything done. Okay, that's all.
We have a bit of time for discussion. Jeff?
Yeah, I'm interested in the question of this critical Rossby number where rotation is, where lost angular momentum is stopped. As I recall, there's a paper, a theoretical paper, I think by Garofalo and Cohen, several years ago, in which they do the following. It's an MHD simulation in which they assume that for a solar type star, there's a spherical harmonic magnetic fields as a function of n and m. So starting with a dipole and going to much more complex. And what they find is that the mass loss rate, when you go from n equals 1 to n equals 10, goes down a factor of 50. Now, if a star does that, in reality, that would really stop the loss of angular momentum. So my question is, have you read that paper, and what's your comment on it?
I think I've skimmed it, so I don't have much of a comment on it. But yeah, so I think that's different than the magnetic topology argument.
What is topology? It's the complexity of the field.
Yeah, but it is topology. So it's topology, but in a different sense. Topology affecting the mass loss, not topology affecting the tethering ability, I would say.
Well, if you stop the mass loss, then you stop the decrease in rotation.
Right. Yeah, I think that's the leading theory behind this. It'll take ZDI observations to see if that's the case.
Anyone else?
In the introduction part, you said there are some long-term activity observations. And are there any TESS target stars in the, so example, Mount Wilson or STSW?
Yeah, all of them. But they're in the north, mostly.
Ah,
So next year.
Next year.
Next year.
Yep. Okay, so it's the north and south ecliptic, which is not the north, so there's overlap in the north and south equatorial, so there's going to be some Mount Wilson stars. In fact, the top one that I showed, HD 20630, has already been observed. So they're coming in the pipeline. It's very exciting.
So I want to ask a question from a sort of physical nonlinear dynamics point of view. So a star is this rotating, self-fueling, conducting, blah blah blah, and it's very nonlinear in fluid dynamics and also magnetohydrodynamics. And so just looked at it from that broad picture point of view, that you could imagine describing it in terms of nonlinear dynamics, in terms of attractors, that it might want to spend a certain amount of time in this phase, a certain amount of time in that phase. So what strikes me about your talk is that, at least when integrated over the whole sun or star, and then looked at as a function of time, I don't see more than one attractor here. I mean, all these stars want to do essentially the same thing. And so that's really remarkable given the complexity of the system we're looking at. So the question is, why is that? Is it because of averaging over the interiors of all these stars? I mean, why would all the stars choose to behave in a very similar way? And that's encouraging in one point of view, in that we got a shot at understanding how the dynamo works on the basis of looking at many, many different stars. It's discouraging from the other point of view, in that I think that maybe magnetohydrodynamics and the gravitational pull and something about these systems forces it to do a certain thing in spite of what it might otherwise do. Do you have a comment on whether I'm statistically on a sound footing to say that? Or
Yeah.
What's your opinion about that if you look at it from that point of view? Do you have a feeling about it?
Yeah, I think you're unfortunately not statistically on sound footing. That the only data that's able to test this kind of thing is like the Mount Wilson data, and it's unfortunately, I think, too small. It sure would be nice to have an order of magnitude more stars with decadal scale time series. The indications are strong that there's at least sort of two main regimes of variability: extremely complex, multi-period variability. Whether you want to call anything like a cycle in those fast rotating, I think, is up to debate. I'm skeptical. And then you have the sun-like stars, which is the sun and a bunch of K stars that have a very clearly defined cycle. And then the sun also doing something interesting, going into the Maunder minimum, flat activity, which is something you also see the high Rossby number stars doing. So those are the sort of two maybe attractors that I see evidence for, but I sure would like to have more data. Yeah.
I think it'd be really interesting to look at M dwarfs. The whole question of do they have cycles or not. If this belief that fully convective stars don't have alpha omega type dynamos, or shouldn't have them, then you might expect something very different in the cyclic limitations.
Mm-hmm.
So,
Yep.
the test, do you think you're going to be able to do this?
Okay, cycles,
Yeah.
decadal scale cycles
Yeah,
with
not
TESS.
really.
You could, actually. There's hope, because TESS is a 2-year nominal mission, but they're going to ask for more funding, and I'm told that they have enough fuel to do the pointing that they're doing for 100 or more years. And so they're fine. So we can get photometric activity for tons of M dwarfs, SPH activity metrics, hopefully for a decade or more.
Okay.
Yeah. I don't know what else can break on TESS. What could possibly go wrong?
I think that will close the discussion. Thank you for you
Yeah, I'm familiar. I started talking about it.
And you need to stop.